I'd like to acknowledge a number of co-sponsors here, of course. Union of Concerned Scientists, Sustainable Energy Resources Group, Sustainable Hanover Committee, Hanover Conservancy, and the Catamount Earth Institute, the Hanover High School Environmental Club, a number of them are here, the Vermont Natural Resources Council, and Building a Local Economy, BALE is here as well. In particular, I wanted to note with the Union of Concerned Scientists, Roger Stevenson is here, and he wanted to make a couple of announcements himself. Roger?
Thank you, Mike. I'm delighted to be here. I'm from the flatlands of Stratham, New Hampshire, where I live. I have the distinct pleasure of taking over for New Hampshire the Union of Concerned Scientists post that Jim Rubens left. He's an Aetna resident. He and I had dinner last night in Portsmouth. He was speaking to the Rye Republican Club. As many of you may know, Jim Rubens from Aetna is running for the Republican nomination for U.S. Senate in New Hampshire. That's not a commercial, just an update. He's been a delight to work with, staunch believer in climate change, science, and action. I've been a resident of New Hampshire since 1976. I've put on your chairs this little postcard of a lobster. I could have put a postcard of the state flower of New Hampshire. Who knows what the state flower is? Thank you. It's blooming 7 days earlier now than it was in 1970. I could have put a postcard of the moose on your chair, but I chose a lobster because they're delicious. And I do want you to consider signing up. I want to give you updates on where your delegation is and where the President's Climate Action Plan is in the state of things. So if you would, please sign up. I promise I won't inundate you, but I do promise to give you valuable, effective information on the state of play of the President's Climate Plan and how you can be involved. Thank you.
As I said, this is the first in a series of discussions we'll be having. We are tentatively scheduling in mid-October. Frank McGilligan and Jonathan Winter, both of Dartmouth, will be talking about is there a working title for that?
There's not a working title. It's on environment and agriculture and water resources.
Environment, agriculture, and water resources. And then on December 3rd, Professor Andy Friedland from Dartmouth will be talking about should we burn wood? And that should be an interesting and provocative conversation. Other announcements, on Monday, September 30th in the Norwich Library 7 p.m., there'll be a happening in Montpelier, a legislature's reports with Senator Richard McCormick, Representatives Margaret Cheney, I assume she'll still be there, Jim Maslin and Kevin Christie will bring us up to date on bills and issues which will be coming up in the next legislative session. It's co-sponsored by the League of Women Voters and the Norwich Women's Club. So tonight we have Brad Marston is going to be speaking with us for about 45 minutes, and then we'll have a question and answer period. And a person very instrumental in having Brad come up here is Professor David Montgomery, and I'm going to have David introduce Brad. So.
Well, nobody here is going to be surprised if I say that climate science is a difficult subject. But you start asking why it's so difficult, and the only answer I can come up with is that there are so many pieces to fit together. There are so many different kinds of science that are involved that no one can get his mind around all of them. I sat down for 5 minutes to list the ones that I could think of. Can you hear me now? I don't think it's turned on. It's not on.
Yeah. It's on, right? Can you hear it? Yeah.
Okay, good enough. So I made a list. I made a list of the branches of science that I could think of that are sort of necessary at some point or other in constructing scenarios for climate science. Hydrodynamics, aerodynamics, meteorology, atmospheric chemistry, solar astronomy, oceanography, geology, molecular quantum mechanics, planetary orbital mechanics, including all the planets, not just one, radiative heat transfer, ionospheric physics, thermal conduction, statistical mechanics, dynamical systems, so all under the name chaos, often appearing. And I could probably enlarge that if I thought about it a little bit. But the problem is that there isn't anybody that knows all those subjects. And the pieces, while taken one at a time, are not so difficult, perhaps. Fitting them together is nearly impossible, and nobody is prepared to do that, which leads to a lot of strife and arguments. People get hot under the collar talking about global warming. And we have tonight a speaker who's kept his cool pretty well throughout all this. Professor Brad Marston from Brown is here. He's been at Brown for about 20 years. He went there after getting his bachelor's degree at Caltech and his PhD at Princeton. He started out in condensed matter physics and switched over to climate science 10, 12 years ago or so. He's been the chair of the Rhode Island chapter of the Sierra Club. And what else do I have down for him? He's also on the XCOM for the topical group on physics of climate of the American Physical Society, which sounds like an innocent sort of an organization, but you'd be surprised at how much strife there was within the American Physical Society, even to get that group chartered. And Brad is a member of the committee that's supposed to tell what it means now.
Okay, thank you. Thank you, David and Michael. The subject of my talk tonight is the science of global warming. I want to just focus on the science as much as possible. And as David indicated, that's really, it's an impossible task to do this comprehensively. We'll touch on many of the areas that David mentioned, but I won't be able to do justice to any of them. But I'd like to give you the big picture of how we understand climate and hopefully gain some understanding of how the climate has changed in the past and may be changing, likely will be changing in the future. So I'd like to acknowledge, before I go any further, support from the National Science Foundation, which has been very generous in supporting my research in climate physics. So if we were standing here 20,000 years ago, it would look something like this. Maybe up here in Vermont, there might be a few peaks of mountains sticking up through the ice cap. But there was a vast continental ice sheet. It's extended all the way down to where I live, Rhode Island, where it was about a mile thick, where my house currently is. And clearly, the climate can do some very interesting and dramatic things. And so if we can gain an understanding of past climate, we may be able to gain an understanding of how the climate will be changing in the future, and that will be one of the themes in my talk. This is just a plot showing the extent of the ice sheet viewed from the North Pole about 20,000 years ago. You can see that it covered New England here and also parts of northern Europe and Asia, a very extensive body of ice. And at that time, the sea level was much lower because a lot of the water that had been in the ocean was tied up in this ice sheet. So one of the things I want to do tonight is to present some simple physics that controls climate. So we hear in the news about these very complicated climate models, and these are rightfully so very important tools for understanding climate and how it might change. But underlying all that, and what gives us confidence in these models, is actually some fairly simple and basic ideas that come from physics, and I'd like to start with those. So if we look at Earth from space, we immediately see that it's reflecting light from the sun, and so we have some sunlight coming in. And some of that light is reflected off of the clouds especially, or the polar ice cap, also the land surfaces. But about 70% of it is absorbed by the Earth and goes into warming the Earth. If that energy didn't leave the Earth would just get hotter and hotter. But of course, what happens is the Earth radiates heat back out into space. So that if we have, say, 6 units of sunlight coming in, we're going to have 6 units of energy going back out, 2 that are reflected right away, and 4 that are the result of the heat being absorbed, the light being absorbed by the Earth and then converted to heat and radiating back out into space. So there's this balance of energy flowing in and out of the Earth. And we can use this to gain an understanding of the temperature of the Earth. But to do that, we have to think broadly. And I want to evoke this quote by the founder of the Sierra Club, John Muir, who was also made some very important scientific discoveries. In Yosemite, for example, he's the one who realized that glaciers played a large role in shaping the landscape. And he said, when we try to pick out anything by itself, we find that it's hitched to everything else in the universe. And there's no better place to see this statement in action than in climate science, because it's truly the most interdisciplinary of the sciences and involves everything. There's also all the biological sciences and ecology, in addition to the physical sciences that David mentioned. All right, so we're going to go back to the basics for a little bit and try to understand something about light. And so to do that, I'm going to tell you a little bit about quantum mechanics, which seems kind of surprising. You came here presumably to hear about climate, but I'm going to start off by telling you about quantum mechanics. But we need to understand something about quantum mechanics in order to figure out the temperature of the Earth. So there's a basic dichotomy in quantum mechanics. It's something very strange that we don't encounter usually in our everyday life. And it's the wave-particle duality. You've probably many of you have heard about that. So let's start by thinking about particles. Think about marbles, for instance. And we're going to do a little thought experiment here. So let's imagine here we have actually a gun, maybe there's bullets that are spraying out in random directions, and we have a plate, and they can only go through these 2 holes. And then they'll hit some backstop, maybe some sand, and we collect all of these BBs or marbles or whatever. And what we find is that some particles go through slit 1 and some go through slit 2. The ones that go through slit 1 tend to end up over here, and the ones that go through slit 2 end up over here. And so when we look at the contribution for those 2 slits, we get a distribution of the marbles like this. Most of them come in around here on our backstop, and some come a little bit further away. So that corresponds to things that we kind of encounter in everyday life. Now let's look at waves. So let's think about water waves. Let's try to repeat this experiment. We'll see a movie where this is actually done. So imagine dropping a rock in a pond, and it'll send out circular ripples of waves. And when it comes, these waves hit these 2 holes. What will happen is you'll get circular ripples of those waves coming out. And then when we look at the waves that come to this wall, instead of getting that nice smooth pattern, what we'll get are this kind of wiggly pattern. It's called an interference pattern. And it's because sometimes the wave crest from this hole meets a trough of a wave from hole 2, and so they cancel. And so this was something that's been known about light for a couple centuries, actually. The strange thing about light, though, is that it manifests both properties. But before we get to light, let's just look at a movie of water waves here. This is a wave tank. We're looking down sort of on an aquarium, and we're going to be jiggling this water here and making waves. These are the crests of the waves, these bright lines. They're going to be hitting this wall that has 2 holes, and you can see this interference pattern coming out. You can see that there's more waves here, and then, let's see, we'll be slower here. More waves here, less, more, less, and so on. It's different than with the particles. Okay, let's try to do this experiment with light. So at Brown, maybe Dartmouth has this experiment too. At Brown, when we're teaching quantum mechanics, we are able to actually do this with light. But you'll see there's a little twist. So here you see an interference pattern, and this is from a laser light that's hitting a little slit. It has two slits, and let's let it go here. And you can see this pattern, but what we're going to do now is decrease the brightness of the light. And we're going to do it until what we see is now just a bunch of particles coming in. Light is made out of particles called photons, just like matter is made out of atoms. And they seem to be random in where they're hitting our screen. But now we're going to tell the computer to take a time exposure of those random particles. And so here's our time exposure. And there's the interference pattern again. So there we see, probably the clearest way, that light behaves like nothing you've ever seen before in your daily experience. It has both a wave-like property and a particle-like property. How can it possibly do this? We can understand waves, how they make these ripples. But here we see the particles of light coming in one at a time. And it's the particles of light are interfering with themselves in some way that we have no everyday experience, no common experience with. We just can't understand that. And that's just the nature of things when we go look at things that are very small or things that are very large in the universe. We also have very strange things like black holes that are not like our everyday experience. So is a photon, a particle of light, is it a particle? Is it a wave? Is it both? Is it neither? Richard Feynman, famous quantum physicists, like to say it's like nothing you've ever seen before. So then he would go on to say, well, how do electrons behave? They also behave the same way, like nothing you've ever seen before, except at least they behave sort of like light. So they have something in common. Now, you've all heard of the equation E equals mc squared by Einstein. But Einstein's actually responsible for another equation, another E equals equation. And this one is actually, it deserves to be better known than E equals mc squared because it's much more profound. E equals h times f. E represents the energy of a little particle of light. F is its frequency. So light has frequency, radio waves have frequency. And h is called Planck's constant. It's just a constant that relates these two things. And so this equation encapsulates the fact that light doesn't behave like anything we've ever seen before. It has both a particle-like property, the energy comes in lumps, that's what we saw, those flashes, and it has a frequency, it behaves like a wave, and they're related by these two things. And when Planck wrote that down, or when Einstein wrote that down, then it was possible to understand how light can warm a planet. So this is the last equation this is the last slide with equations, and you don't need to, if you don't follow this, that's okay. You'll just get the gist of it. Everything after this is going to be gravy. So let's apply this to calculate the temperature of the Earth. So it turns out that if you have a body that's at some temperature, T, that the intensity of the radiation it gives off, the heat it gives off, is proportional to the temperature to the fourth power. And you've all experienced that if you have a burner and you slowly heat it up like an electric burner on a stove, it starts glowing red and it gives off heat. But as its temperature increases, it gets much brighter. And so its brightness increases rapidly with its temperature. We need this constant. And we plug it into a formula that uses the solar radiation. The sun gives about 1,366 watts per meter squared on the surface of the Earth on a flat plane. This is the reason why solar power works. And about 30% of it, as I mentioned, reflects back out into space. So we subtract that. Only 70% contributes to this temperature. And we calculate the temperature of the Earth, and what we find is that we should be freezing. It should be about 0 degrees Fahrenheit. So it looks like a pretty spectacular failure. But in science, as in life, a failure is often more instructive than a success. And we're going to see that this failure is telling us something very important about planet Earth. And we can learn about that if we compare Earth to its two neighboring planets, Venus and Mars. Because very conveniently, the solar system has provided us two opposite extremes. Earth is in the middle, literally in position, but also in terms of its temperature between these two other bodies. So let's look at these other planets. So here we have a little table. The planet, our calculated temperature that we just did for Earth, the actual temperature for Earth, and the difference between those two I'll call the greenhouse warming. So Earth, we said, was about 0 degrees Fahrenheit by average, but in reality it's about 60 degrees Fahrenheit. It's hotter in the equators, colder in the poles, but average is out to about 59 degrees. So the difference between those two is 59 degrees. Something else is warming the Earth by that amount. Now let's look at Mars. From our formula, Mars is even colder than Earth because it's farther from the sun than Earth. It's about minus 70 degrees Fahrenheit. And the actual temperature of Mars is pretty close to that, about minus 63 degrees Fahrenheit. So there's very little difference between those two. So our formula actually works remarkably well for Mars. And the reason for that is because Mars has a very thin atmosphere. It's almost, if astronauts ever go there, they're going to have to wear spacesuits because otherwise their blood would boil. The pressure there is 100th that of Earth. Let's look at Venus now. Venus actually has a lower temperature than Earth, even though it's closer to the sun than Earth, not because of the distance, but because it's completely covered with clouds. That's why it's such a brilliant planet in the morning or evening sky. It reflects 3/4 of the light hitting it. So if that were all that were happening, Venus would be colder than Earth. But the actual temperature of Venus is about 800 degrees Fahrenheit. And the reason for that is that the Venus atmosphere is almost 100 times thicker than Earth's, and it's nearly 95% carbon dioxide. So carbon dioxide is providing a gigantic warming of Venus. And so it's just, you could hardly hope for a better example of the greenhouse effect in action of carbon dioxide raising the temperature, in this case, of the planet to levels far beyond what could support life. So Venus is our opposite extreme, and it's basically an Earth gone bad. What happened to Venus probably is that it lost its water, and when the planet lost its water, it lost the ability to absorb carbon dioxide into the rocks. And so all the carbon dioxide that was emitted from volcanoes on Venus went up into the atmosphere instead of going back down into the rocks like it did in Earth, leaving the big carbonate limestone that we have around Earth. Now, on Venus, carbon dioxide is the main greenhouse gas, but in the case of Earth, actually water vapor is the most important, and that has some interesting implications. Carbon dioxide is the second most important. Now, just to say that Mars does have a thin atmosphere. You can see it here in this view from a satellite on the limb. It's actually, there's dust that's giving it this reddish color, and the dust can warm the atmosphere of Mars slightly, especially when there's large dust storms which cross the planet occasionally. Now let's look at these gases in our atmosphere. So now we're going to think about some chemistry, some molecular physics that David mentioned. Here's our water molecule. And the important thing about water is that it's a polar molecule. The hydrogens have a positive charge, and the oxygen has a negative charge, H2O. And that means that water vapor can absorb and emit infrared radiation, heat, very efficiently, and this is why it's a greenhouse gas. Carbon dioxide is similar. We have a carbon surrounded by two oxygens. The carbon is positively charged, the oxygens are negatively charged, and when light, when heat from the Earth tries to go out into space, it can cause these atoms to vibrate and absorb the infrared radiation, and then that molecule can give up the infrared radiation and send it back down to the Earth, warming the surface. And this is the reason why if you go to, say, a desert, a high desert, where there's not much water in the atmosphere, you know that there'll be very strong temperature swings between the day and the night because there isn't much water vapor to send the infrared radiation back down to the ground at nighttime, and we get a lot of cooling. Or that even here, when the humidity is low, the night will cool off a lot more than when the humidity is high. Now, the main constituents of the atmosphere are nitrogen, about 78%, oxygen, about 21%, and argon, 1%. And all three of these molecules differ from these two because there is a symmetry here. There's two nitrogens or two oxygens, so there's no charge here, no charge difference. These aren't polar molecules, and so they're transparent to the infrared radiation. So these guys, the main constituents of our atmosphere, don't give us any of this warming effect that these two gases do. And this is why so much attention is paid to these two molecules. Now, there's a very important difference, though, between carbon dioxide and water, and that is a water molecule only stays up in the atmosphere for a few days before it rains out. But carbon dioxide, when we emit carbon dioxide from burning fuels, it stays up there for a long time. So the carbon dioxide we're emitting now will tend to stay up in the atmosphere for centuries. And so this is the one that really controls the climate, and the water kind of responds in a way that amplifies the changes from carbon dioxide. And I'll talk about that a little bit more in a moment. So this is a movie of planet Earth from October 2007. And it's one of these infrared pictures. So it's looking at the heat escaping from the planet. And I defy you to tell me where this satellite is situated above the planet. Over what continents is it situated? You can't tell because the light coming out of the surface has been completely obscured by the water in the atmosphere. So what we're seeing is the water vapor, and we don't see the surface of the Earth because that water vapor is such a powerful greenhouse gas that it has absorbed any infrared radiation leaving the surface, and what we see instead is the upper layers of the atmosphere where the water vapor finally gets thin enough so that the photons can go out and reach the satellite. Now, beyond just that, we can see some very interesting properties of the atmosphere. You can see there's a very striking difference between the tropics, which is this region, and the extratropics. For one thing, this kind of pulsing you're seeing, that's the thunderstorms that build up during the day in the tropics and then calm down at night. This is over several days, and it's repeating in a loop. Up at the high latitudes, such as in Vermont and New Hampshire, we have the winds that are blowing mainly from the west to the east, the westerlies, but there's a lot of curling around, and those are the storm systems. Similarly, in the southern hemisphere, the winds blow from the west to the east. But you can actually see the trade winds in the equatorial regions. If you follow some of these pulsing thunderstorms, you'll see that they're drifting from the east to the west. So we can see that the winds are blowing in a different direction at low latitudes than at high latitudes. The atmosphere is doing some very rich things, and one of the important things that it's doing is it's redistributing heat from the equatorial regions where the sunlight is most intense up to the polar regions, and I'll touch on that a little bit later. Now, just to emphasize again how important water vapor is, this is a view of one of the astronomical observatories on top of Hawaii, so at an altitude of over 14,000 feet. And this observatory here has a special telescope that looks at objects in the infrared band, or in the longer wavelengths than the eye can perceive. And the reason it's up here is to get it above the water vapor. And you can see, in fact, that the water vapor is mainly down here. Here's another one of the Hawaiian Islands. But most of the clouds and moisture are below this 14,000 foot elevation. So this elevation is where the infrared photons can still come in from space and be seen by the astronomers. So we calculated the temperature of the Earth was about 0 degrees Fahrenheit, but we know the surface is about 60 degrees Fahrenheit on average. So what does that 0 degree Fahrenheit correspond to? It corresponds to the temperature of the atmosphere about 5 kilometers up in elevation, 5,000 meters. That's the point where the infrared photons can go out into space. And we can use that understanding to make a very simple calculation of how much the temperature of the Earth will increase as we double the concentration of carbon dioxide. So before human beings began their industrial production of carbon dioxide by burning fossil fuels, there was about 270 parts per million of the atmosphere were carbon dioxide. Does anyone know what it is currently? What? It's getting close to 400 parts per million. And sometime in the middle of this century, it'll be twice 270, so about 540 parts per million. So climate scientists often talk about that scenario where there's been a doubling of the amount of carbon dioxide concentration. And what's going to happen when we get to twice the pre-industrial level is that this height at which the photons can go out into space will increase by about 150 meters. Now, up at 5 kilometers, the air is at 0 degrees Fahrenheit. And we know that the air gets warmer as we go lower. It gets warmer by about 6.5 degrees per kilometer. So if we take that 6.5 degrees per kilometer and multiply it by 150 meters, the increase in this height, then we would deduce from that the Earth would warm about 1 degree Celsius from this doubling of carbon dioxide. Now, 1 degree Celsius wouldn't be cause for some concern, but by itself, that's not, wouldn't be too worrisome. People are talking more about 2 or 3 or 4 degrees of warming from a doubling of carbon dioxide. So where is that amplification coming from? It's coming from the fact that as the Earth warms, more water will also go up into the atmosphere. As the oceans get warmer, then more water will evaporate. And that water is a very strong greenhouse gas, and that will further increase the warming. So that's actually the main mechanism by which the relatively small warming due to carbon dioxide emissions from human beings is amplified naturally to the larger numbers of several degrees Celsius that people talk about coming from the very complicated models. And actually, this estimate is just as good as the most complicated models. It hasn't basically improved for the past nearly a century when the first calculation along these lines was done. It's been very little improvement. And the reason for that is because of the complexity of the climate system. Now, I'd like to come back to the ice ages. This is a reconstruction of the temperature of the Earth over 800,000 years based on some ice cores that were drilled in Antarctica. So down below, or up above here, is the temperature. This is the present time, and this is 800,000 years ago. So this is the present warm period, and this was the last ice age. So this is 20,000 years ago when there was ice covering all of New England. And this is a previous warm period, and then another ice age, warm period, ice age. You can see there's been a succession of ice ages and warm periods. Down here is the carbon dioxide concentration of the Earth over that same period of time. And there's a remarkable match between these two. So even over here, if you look at this kind of complicated feature, you'll see the same sort of signature in the carbon dioxide and in the temperature. So it's likely that whatever is causing the ice ages, whatever causing the succession of ice ages, is being amplified by the Earth's carbon cycle, by the carbon that's contained in the oceans and the atmosphere, so that there's more carbon in the atmosphere when it's warmer, and probably that carbon is causing it to be warmer. So this is another example of what we call a positive feedback process. We already talked about one, the water vapor, more water vapor when the Earth is warmer, causing it to warm further. This is evidence that there's more carbon dioxide when the Earth is warmer, causing it to warm further. But what causes these ice ages in the first place? Well, the answer is the Earth's orbit changes over time, and it changes in three crucial ways. The first is that we know that the Earth's orbit is not a perfect circle. It's really more of an ellipse. And the degree to which it's elliptical oscillates with a period of about 100,000 years and also another period of 400,000 years. And that's because of the tug of Jupiter and Saturn, because they're so massive, they pull the Earth's orbit by gravity, and Venus because it's so close. We also know that the axis of rotation of the Earth, which right now points very close to the star Polaris, what we call the North Star, that also changes over time. So that in the time of the Egyptians, it was actually pointing towards a star called Alpha Draconis. And finally, the tilt of the Earth's orbit changes over time. So right now it's 23.5 degrees. That's where the tropics of Capricorn and Cancer are located, but that oscillates with a period of about 41,000 years. Because of the tug of the other planets. These orbital variations are very likely what are setting the time of the ice ages, the timing of the ice ages, especially this one, that they're coming every 100,000 years or so, or they have been. They have been for the past million years. If we go back further in time, they came every 41,000 years. Which is the time of the tilt of the Earth's axis. So there are some interesting changes going on. Now, when you look at a plot like this, with this vast stretch of time, sometimes people say, well, this just shows us weather goes in cycles, and so, well, the climate will change in cycles, and maybe it's warming now, but it'll cool later. But it's very important to recognize what a vast stretch of time this is. 800,000 years has no meaning in terms of human existence. For example, the Roman Empire 2,000 years ago is this, just right at this point here, and that's 100 generations in the past from now. We can't comprehend even the time period of the Roman Empire. This is a much vaster period of time. So these kinds of oscillations, although they teach us a lot about climate, are not directly relevant to the type of climate change that we're talking about right now, which is a much more rapid thing. It's happening 1,000 times faster than this kind of oscillation. Now, one thing we can do, well, so here's our plot of our carbon dioxide that everyone here seems to be pretty well knowledgeable about. So it was first measured very precisely back in 1958. And it's been growing steadily. It actually oscillates over the course of a year because during the springtime, as the plants leaf out, they absorb carbon dioxide, so the amount of carbon dioxide in the atmosphere drops. And in the fall, or now, they give up their carbon as the plants, the leaves decay, and it goes back up into the atmosphere. And since most of the plants are in the northern hemisphere, where most of the land is, then it's driven by the northern hemisphere. So now this plot stopped around 2009, but now we're getting close to 400 parts per million. Now, we can use what happened to the Earth during the Ice Age to come at another independent estimate of how much the Earth will warm due to the added carbon dioxide. And the logic is as follows. We know that the Earth was about 5 degrees Celsius cooler, so 9 degrees Fahrenheit cooler on average during the depth of the last ice age, 20,000 years ago. It was about 9 degrees Fahrenheit cooler. We also know that, as we saw, there were less greenhouse gases then. There was less carbon dioxide. Some of these other greenhouse gases like methane were also reduced. And furthermore, the ice sheet was bigger because down here, Norwich was covered under ice, and so the Earth reflected more light out back out into space. It wasn't absorbed. So that tells us how much a change in ice and greenhouse gases changes the temperature. That much change in the ice and the greenhouse gases changed the temperature by 9 degrees. And so that gives us a prediction for how much the Earth will warm if we, say, double the carbon dioxide. And that prediction gives us the same sort of number, 2 to 3 to 4 degrees of warming, as our completely independent calculation that we just did gave us. So here, we have something very nice in science. We have two independent lines of reasoning giving us the same number, and they both are simple calculations. They don't rely on some complicated model that no one person understands. Here we can understand this calculation. I'm going to skip through this, I guess. This is just a calculation of the temperature of the Earth, taking into account the water vapor, the change in the water vapor, more water going up as the Earth warms, less ice and snow, some changes into the clouds. This is now a projection. Well, here we see a reconstruction of the Earth's temperature, the temperature of the northern hemisphere, to be precise, from 1,000 years ago, 81,000, up to 2,000. During this time period, from about 1880 on, we have enough thermometers around the world that we can reconstruct the temperature directly. Before that, we have to use tree rings and ice cores and cores drilled into the Earth to do that. And you can see the temperature over this 1,000 years was fairly steady. There was a little bit of a drop towards the, in 1700s to about 1900, maybe going back a little bit further, called the Little Ice Age, which I'll have a few words to say about it in a bit. But it's fairly stable, with some increase in the 20th century. What sort of projection are we looking at for the 21st century? Something like this, way outside of the natural bounds. Now, this comes from the IPCC, the Intergovernmental Panel on Climate Change, from over 10 years ago. They're about to release another report at the end of the month. But this estimate has barely changed. And a lot of this uncertainty here depends on what humans do, because it's different scenarios for how much carbon dioxide we choose to put up into the atmosphere. If we choose to make that a priority, the temperature will be lower. If we choose to not make it a priority, the temperature will be higher. Some of this spread is also from the uncertainty in the models, and I'm going to now talk about some of the sources of the uncertainty, why it's been so difficult to improve our estimates. We know that the temperature will go up, but to really pin down how much it will go up has been a very difficult problem. Here's actually the actual blow-up of the temperature of the past, during this time period when we have enough thermometers. And you can see the red here is the northern hemisphere, and the blue is the southern hemisphere. And there's been an interesting divergence of these two. Certainly the temperature fluctuates a lot from year to year. So there's a lot of variation just due to the weather. But there's an upward trend. And there seems to be a splitting away of the northern hemisphere from the southern hemisphere. This may be because there's more land again up in the northern hemisphere. In the southern hemisphere, we have those vast oceans which tend to ameliorate the effects of warming, because the oceans can absorb the added heat for a period of time, slowing down the warming more than the land can. But this is an area of active research, understanding the difference between these two. So now let's talk a little bit about the actual complexity of the climate system. A snapshot of the Earth immediately reveals the complexity, because we have the land surfaces, which vary in their brightness. So the African Sahara Desert is very bright, whereas the tropics have the plants that are absorbing light. So there's all this local variation. And then there's the clouds that are rich and have lots of fine structure, especially in the tropics. We have all these little thunderstorms. In the extratropics, we have these waves of storm systems. These are what bring the succession of rain and clear days during up in the mid-latitudes, such as here. There's clearly a lot of complexity here that needs to be understood. The clouds, well, so let me talk about the dynamics first. I mentioned that the atmosphere transports heat from the equator to the poles, but the details of how it does that are not fully understood. Models reproduce that, but they reproduce that the basic features, but some of the subtle features are not understood. So for example, at around 30 degrees north or south, we have deserts. And that's because there's sinking air at these points. And sinking air tends to dry as it drops. As it moves down from high altitudes where it's cold and dry, it comes down and warms up, but it's still dry. And so that's why we have deserts at these latitudes. Well, we can ask, will the location of these deserts change as the climate changes, as the overall temperature of the Earth changes? We don't really know the answer to that. Based on the experience of the ice ages, it seems that we might expect that these desert regions could expand moving northward. So for instance, the Great Salt Lake in Utah during the Ice Age 20,000 years ago was filled to the brim with water. In fact, it was filled so high that it cascaded down the Snake River. So it was much wetter then, and it's been drying as the Earth has been warming, and perhaps that will continue. If you're interested in playing around with the circulation of the atmosphere, and if you own an Apple computer, I have put for free my research tool, which you can use on the Mac App Store. And you're welcome to download it. It's called GCM for General Circulation Model. And try it out. You can get all sorts of circulations similar to the ones that we saw on the Earth. And I don't have time tonight to tell you about the details of this model, but you might enjoy playing around with it. And I think it's kind of fun. All right, besides the problem of the circulation, there's also the clouds. And the clouds come in three basic types. We have these high cirrus clouds. These clouds are very cold, so they don't give off much heat to space, but they let sunlight through. So they're very good at warming the Earth. The sunlight comes in to warm, but since they're cold, they prevent infrared radiation from going out into space. By contrast, fog or stratus clouds does the opposite. It's low. You can see here it's below the Golden Gate Bridge, so it's warm. It gives off a lot of radiation to space, and it reflects a lot of sunlight. So stratus clouds cool the Earth. Cumulonimbus clouds do both because they're kind of a combination of cirrus clouds and also low clouds. So this is the worst sort of situation for a predictive science because we have competing effects. Some clouds warm the Earth, some clouds cool the Earth, and how the clouds will change as the Earth warms is a great source of uncertainty. Actually, it's probably the biggest source of uncertainty in climate modeling because it's very difficult to model clouds. If you're trying to model the whole Earth and you need to get these little structures in the clouds, that's far beyond the capability of any supercomputer nowadays, or even probably 150 years in the future. To get all these ripples here and yet describe the whole Earth at the same time. Another source of complexity is the ocean. The ocean circulation is even more rich than the Earth's circulation. Here, this is a reconstruction. This is Hurricane Katrina has just passed, and this is the Gulf Stream that supplied the warm water that powered Hurricane Katrina as it hit New Orleans. And we see the Gulf Stream, and you see all of these fine vortices and structure coming along the continents, especially coming off of Cape Horn in Africa. There are these whirls spinning out. These are although a computer was used to produce this, this is based on actual data. Now we're up to August 2006. You can see the structure of the ocean is finer than the structure of the atmosphere. The atmosphere basically has those two types of motions. We have the trade winds and the westerlies at high latitudes. Here, things are going all over the place. And getting the details of this right is essential to improving our estimates of climate, because the ocean is interacting very strongly with the atmosphere, giving up heat and absorbing heat. Here's the current coming off of Japan, and then it basically dissipates into the Pacific. Something else that has been subject of a lot of interest because it seems to be occurring is something called polar amplification of warming. The warming that has been going on has been greatest in the northern hemisphere at high latitudes. This is actually a model prediction, but I'm sure you've heard that the sea ice up in the Arctic Ocean has been decreasing, and so in fact last year it reached its minimum, and the famed Northwest Passage opened up. It's possible that this sea ice will actually disappear during the summer months within a decade or two. No one really knows. And one of the effects of this sea ice disappearing is that this ocean that's now exposed during the summertime can absorb the sunlight. We reduce the reflectivity of the Earth, and that accelerates the warming of the high latitudes, and that seems to be what's driving this polar amplification. And already ecologists have noticed that in the high latitudes, plant growth has been accelerated because of the greater warmth and also probably additional carbon dioxide. So this is a reconstruction of how the forests in the high latitudes, the boreal forests, are growing rapidly during the summertime, more rapidly because of the warming. Then I mentioned that the dry regions of the Earth may expand northward. One of the reasons for that is that it's predicted that the jet stream may move northward as the Earth warms. And there may be other ramifications of that movement. For example, the storm track will change, and so the location and the intensity of storms may change with it. So there's been a lot of focus on the Earth's average temperature warming, and certainly that was the focus of the first part of my talk. But that average temperature of the Earth is not the thing that really matters to human beings or to other forms of life on the Earth. It's really the extremes and the amount of moisture. So if the average temperature of the Earth goes up a few degrees, who cares? It doesn't seem like such a big problem. But it's what that implies in terms of the other things that will change, such as the motion of the air, where the precipitation falls, and the intensity that it falls, and so on. These are the things that are really of concern and are harder to understand and model. So this is a painting that was hanging in the Rhode Island School of Design. A mural is hanging in the Rhode Island School of Design a few years ago called Manifest Destiny by Alexis Rockman. And it's an imagining of what the Brooklyn Bridge might look like 1,000 years from now or so. The sea level has risen considerably. Maybe the part of the Antarctic ice shelf has collapsed. It hasn't risen the full height that it could, because if we melted both Antarctica and Greenland's ice cap, the water level would go up nearly 300 feet. And this is, an imagination, obviously, but something that you could imagine happening not in the next decades or even centuries, but perhaps in millennia if the carbon dioxide keeps on going up and nothing is done about that. Okay, so I know a lot of you are probably avid hikers, and so I can't resist telling you a little bit about a summer adventure I had, and I'm going to talk about it in the context of climate. So this summer, I took a month off and I hiked the John Muir Trail. And so the John Muir Trail starts from Yosemite Valley, and it goes 220 miles from Yosemite along the spine of the Sierra Nevada through the Ansel Adams Wilderness and the John Muir Wilderness into Kings Canyon, and then it ends up at Mount Whitney. So I thought I'd leave you on a high note by telling you just a little bit about this hike, which was such a wonderful experience, and showing you a few climate-related slides along the way. I won't torture you with too many slides here. This is just an elevation profile of the hike, starting from about 4,000 feet in Yosemite Valley and going over a succession of passes, ending up at Mount Whitney, the highest point in the continental United States. So we did about 46,000 feet elevation gain and loss over that period, which I'd never done anything quite like that, and I wasn't sure I was going to be able to do it. But just taking it day by day, it wasn't as bad as I thought it would be. Now, one of the things I visited along the way is the highest point in Yosemite, Mount Lyell, and this is a view of the glacier at Mount Lyell in 1883. So, about 130 years ago or so, 1883, and so that's a picture from back then, and this is my picture of it. So it used to basically extend almost all the way down to the John Muir Trail, covering this. And now it's just this small remnant, and probably rapidly dissipating. Now these glaciers, these living glaciers in the Sierras, are actually relatively recent. They're an artifact, or they grew during the Little Ice Age. So before the Little Ice Age, the planet was a bit warmer, and probably the Sierras didn't have any glaciers. So the glaciers are relatively recent phenomena, and the Little Ice Age, during the Little Ice Age, which we don't understand why what caused the Earth to cool in parts for a few centuries. There's a number of interesting ideas. But anyway, the Little Ice Age is definitely over, and as the Earth warms, this glacier is disappearing very quickly, and maybe in a couple decades it'll be gone. This isn't really climate related, but it's just pretty. So they're magnificent flowers. It's the best flowers I've ever seen. This past summer was the driest summer on record in the Sierras. Yet even so, there were some very beautiful wildflower displays. This is one of my favorite spots. This is Mount Banner and Mount Ritter, and this lake is called a Thousand Island Lake at its base. And these are also some smaller glaciers on the mountain. This mountain is about 13,800 feet high. We're going south from Yosemite, and so this is in the Ansel Adams Wilderness. Then we passed into Devil's Postpile, which had been subjected to a very strong windstorm. Estimates were the winds had been up to 200 miles an hour in 2011 and knocked over these gigantic trees, just flattened them for miles. At this time, when I was going through here, there was a lot of smoke from a forest fire called the Aspen Fire, not the Rim Fire that you've probably heard in the news. There was a previous fire that had been set by thunderstorms. And this whole area is volcanic. This is all pumice. And then there's all these burned and down trees. So I felt like I really was passing into hell. So I went into Devil's Postpile here. It was really, this part was quite bleak. So they had some nice, in the National Monument, some nice discussion about climate change in the Sierras, and they have some highly instrumented stations there measuring the climate. Here's top of Devil's Postpile, which, for those of you who don't know, it's a basaltic volcanic flow. It's from lava that flowed and cooled and made these hexagonal patterns. And what's happened here is the glacier has sheared it off, so it leaves these tile-like patterns. So we see the evidence of the glaciation. This is a cinder cone. There's a lot of volcanic rocks, and well, this is basically a volcano. It's a Mammoth Mountain is a volcano that's very close by, and I just was struck by the contrast between that and the lush meadow below. This thing is called a rock glacier. So what's going on here is that there's all these giant granitic boulders, but underneath is a core of ice. And nobody has figured out how to drill into these rock glaciers. They move in a plastic motion. Here's the trail here. And if we could do that, if somebody has a clever idea for drilling and getting cores of these rock glaciers, we could probably get some very interesting climate records out of them. This is just a movie of Wanda Lake. This is named after one of Muir's daughters, and it's right below Muir Pass. And I was just struck by the clarity of the water. So here's Muir Pass. This hut was built by the Sierra Club. We'll see a plaque in just a moment. It's a place that hikers can seek shelter if there's a storm. So this pass is around 12,000 feet, and this is a panorama looking to the north. And this is just a plaque. So it was built in 1931 by the Sierra Club. You couldn't do this nowadays because it's in the wilderness area, but it's grandfathered in. To John Muir, lover of the range of light, this shelter was erected through the generosity of George Frederick Shorts. Now, heading towards Whitney, there are these trees called foxtail pines that are closely related to bristlecone pines trees, which are the oldest living trees on Earth. These ones can live to be 3,000 years old. So they're a nice source for climate records from cores, although I don't know how much work has been done yet in extracting these cores. And this is just my final shot. I climbed up Mount Whitney in the dark, starting at 2 a.m. with headlamps, so that we could get up to the top and see the sunrise. And it was really, really special. So thank you very much.